Hi everyone, I hope that you can see me and hear me. So, welcome to my flat. I hope that you are all healthy and staying at home. You probably heard that we will be staying at home for at least a month. So, in order to keep on schedule all the lectures and labs, I will create a short video so that you get all your information. How I intend to do it, as you can probably see, I'm using QuickTime to share my screen, and I'm also sharing my camera. So you can see me. As you can see, we also have a small blackboard here, and whenever I'll be using it, I will probably maximize the camera so that you are able to see this well. I'm still struggling to get a projector into my flat so that we can project the slides on a wall, but let's see how that goes. So what's the plan for this week? Please don't forget that homework 1 is due next week. If you have any questions or comments regarding that, please post them on Piazza. Then Grand Graph Challenge was due on Monday. We should discuss that. Then we have two topics for today. One is discussing the importance of links in a network, and the other one deals with small world networks. Finally, I have to tell you a bit more about your course project, and we will also discuss exercises that were intended for labs this week. Since these videos are probably going to be very large files, in order to make things more manageable, I will make a short video for each of the topics here. So first starting with this announcement part. Now maybe we can move back to the slides. Yes, I told you homework 1 will be due next week. Homework 2 will be out in 2 weeks. We will discuss the reports and the Graph Grand Challenge today. And please, of course, don't come to the faculty. There will be no lectures or labs in class. So let's first talk about the Grand Graph Challenge. I believe that around 10 or 15 people submitted the challenge, so thanks for that. I believe that the largest network that you were able to, the largest graph that you were able to generate and analyze in roughly 1 minute was around 20 or 30 million nodes, so that's great. So if we look at the PDF, just a second. The first question was asking you what is the expected fraction of nodes in the largest connected component. Since the average degree in the network is log m divided by 4 for sufficiently large n, you expect that the average degree will be at least 1, so you expect to have one giant connected component. Since the average degree is increasing with n, the size of the largest connected component will also increase when you scale to larger networks. And finally, we are not yet in the fully connected regime, which will be where the average degree equals the logarithm of n, so we still do expect to have some small connected components. Now, looking at the times of my implementation, you can see that the graph construction and the search time for finding the largest connected component scales roughly linearly, which is expected because the algorithms that we are using are, of course, linear. Notice also that constructing the graph usually takes more time than analyzing the network. There are multiple reasons for that, although that both algorithms are linear. For once, I mean, in the case of graph construction, you are not only reading from your main memory, but also from your hard drive, which takes longer, and also when you are constructing the graph, you're also writing to the memory, whereas in the case when you are just looking for the largest connected component, you are mostly reading from the memory. And I was expecting to see the same linear scaling also in the submissions that you submitted. The main idea of this challenge was to realize what is the key factor for you to scale to large networks. I mean, is it the algorithm, data structure, programming language, or processor speed, and so on and so forth. Obviously, you have to use fast algorithms. I mean, if you made some if your algorithm was not scaling linearly, you will not be able to scale to really large networks. There are some examples of people submitting their solution where they can only scale to a couple of thousands of nodes, which is not really impressive. Secondly, of course, you need to use efficient data structure. That also goes without saying. But beyond that, it turns out that the main thing in order to be able to scale to large network is the programming language. I mean, I believe that you could never scale in Python to the size of the networks that I was able to do in Java. The best solution submitted was in C or C++. So to reiterate, algorithms, data structures, and the programming language. Of course, it's also important that you have a fast processor, but that only makes you scale to a bit larger networks, not to go another order of magnitude higher. I also created Python implementation that I believe is roughly the most efficient what you can do in Python. Let's look at that. The code for this is available online at the standard location. So let me just click on, I will make this a bit smaller. Let me click on some random link at EU Chilnica, and of course my web page is down. Sorry for that, but otherwise if you type grant .py here, you should be able to access this code when it becomes available again. So the code basically includes just 3 functions. The first one creates the Erdos-Renyi random graph with n nodes and m links, which is represented by a simple adjacency list and in Python implemented as a list of lists. Notice that I'm not bothering with creating parallel edges, loops, and so on, for the case of efficiency. Then the next function here called CC basically takes the adjacency net matrix, adjacency list of a network, and also unvisited nodes, and finds the size of the next connected component of a randomly selected node. So I simply first find a node that is not yet selected, was not yet analyzed, so we don't know in which connected component it goes. And notice that this data structure N is basically a list of booleans that basically just tells me which nodes I have already seen and which I have not. In labs, we probably work with the set data structure, but then that takes adding and removing, mostly removing elements from the set. So I believe it's much faster that you simply use a list of booleans. Then the next few lines just finds the size of the connected component of a randomly selected node I, and returns its size. Obviously, we are using that for search for the reasons that we have discussed in class, and that's more or less it. And finally, the final function that I have here, LCC, which stands for largest connected component, first initializes all the data structures and variables that we need, and then until there are still some nodes to analyze, I find the size of the next randomly selected connected component, and I check whether it is larger than the currently largest connected component, which is stored in this large C. And I can also finish early when the size of the largest connected component that I have already found is larger or equal to the remaining size of the network. And this is basically it. So here at the bottom, I have a simple for loop that for different sizes of the different numbers of nodes computes the average size of the largest connected component over 5 iterations in order to make the results a bit more robust. And so you can download this code and try it on your laptop. On my laptop, I am able to scale to around 7 or 8 million nodes or something like that. There should be a log file, just a second, grand log. So you can see I can do 5 million nodes in roughly 45 seconds, and let's say 7.5 million nodes in roughly a minute. The default implementation in Network X, which most of you are using, will probably scale to like 4 or 5 millions, a bit less than this implementation, and probably the main reason is that the data structure that holds your graph is implemented with dictionaries, not standard lists. And so this is basically it regarding the Grand Graph Challenge. If you have any questions about this, please post on Piazza. So let me make the camera larger. So we have now take care of these first two topics, and I will now pause the video, publish it separately, and create a separate video for link bridging. So thank you for listening.